chapter 7 this morning or this week. So we'll have a lecture on the rest of chapter 7 now, and then in the tutorials on Friday, we'll do further work on it, and hopefully then leave that next week clear then to start chapter 8, the final chapter. Okay. So what have we done in chapter 7 so far? Well, in chapter 6, we introduced the notion of trying to solve a polynomial congruence. We tackled the simplest possible case, which was the case of linear congruences. Linear congruences just being equations AX equal congruent to B, modulo something, modulo n. We got a complete understanding of that. Complete understanding of when this had solutions, when it didn't, and when it did have solutions, exactly how many solutions it had. And it was based on the GCD of A and N, the coefficient of X and the modulus N, and whether or not that D divided B. If it didn't, there weren't solutions. If it did, there were solutions, and there were exactly D solutions. So complete understanding of linear congruences. Then we came to chapter 2 on polynomial congruences, and the first result we looked at, which was last week, was this nice theoretical result due to Lagrange, which places an upper bound on the number of solutions that a polynomial congruence modulo a prime might have. Okay? And this upper bound is nicely provided by the degree of the polynomial. So a polynomial of degree n, which this one is here, because it's sum of f powers x to the I from I equals 0 to n, so it's of nth degree. And it is genuinely of nth degree because it has a non-zero nth coefficient. an, the coefficient of x to the power n, we need to make it very clear that that's non-zero modulo p. So it is a genuinely degree n polynomial congruence. If the leading coefficient an was divisible by p, we wouldn't really regard it as being a degree n polynomial congruence because the coefficient is really 0 modulo p. So we require that it's non-zero modulo p. And then this degree n provides an upper bound on the number of solutions. Okay, it can have at most n solutions modulo p. Okay, so now we come on to this result here, Theorem 7.2. It's quite a technical result about how to go about, well, this is the main kind of tool in how to solve a general polynomial congruence. So a general polynomial congruence will be something like f of x congruent to 0 modulo n. I've given this explanation a few times already, so I'll just give it. We'll give it again here because it explains why we're looking at this result in particular. Now, the general solution procedure is going to first decompose n. Decompose n in the standard kind of number theory way. How do you decompose an integer? Well, you look at its prime factorization. Every integer has a unique prime factorization. It's written as a product of prime numbers. This is the standard kind of set notation we normally use to write that. So it's the product, n is the product of powers of primes p1, p2, all the way up as far as pr, say. And these primes are distinct. So the pi are distinct primes. Every integer can be written like that. Fundamental theorem of arithmetic. And what we're going to do is, if we want to solve this general polynomial congruence, f of x congruent to 0 modulo n, what we're going to do is we're going to solve each congruence here. Solve each congruence here where we're looking at f of x congruent to 0 modulo pi to the power alpha I. We're going to solve each of these congruences for I equals 1 up to r. Separately, not as simultaneous congruences or anything. Just look at this separate family. These got a bunch of separate problems, r separate problems. One problem for each value of I. Okay. So solving these will yield solutions. Maybe yield solutions x congruent to something modulo pi to the alpha I. Let me call them solutions S. Now bear with me, I have to use a double index here. We get solutions Sij. So you get some bunch of solutions, and J, there'll be a certain number of solutions for the ith one of these, for f of x congruent to 0 modulo pi to the alpha I. So let's say the J runs from 1 up to m sub I. So m sub I is the number of solutions to this one here, to that ith problem. Let's put a may yield solutions. We may find that one of these has no solutions at all. These may yield solutions like this. And then from these sets of solutions, Sij, we can take a selection of x congruent to, say, one of the S1s. This is modulo P1 to the alpha 1. X congruent to one of the S2s, modulo P2 to the alpha 2. Modulo PR to the alpha R. So having found all these solutions to these R different problems here, when you take when you extract one solution for each one of these, stick them down on the page by the Chinese remainder theorem. The Chinese remainder theorem, these give you one single solution, single unique solution, modulo. Remember, the Chinese remainder theorem gives you one simultaneous solution to those modulo the product of all the moduli. Of course, when you multiply together all those moduli, what you get n. You get this number n. So this is how you obtain your solutions to the original problem, f of x congruent to 0 modulo. You split it up into this family of sub-problems, modulo each of the prime powers, the powers of primes. Look for solutions of those. If you do find some solutions for each of these, then you can take a selection of them. So this is going to be J1, J2, some values of the second index up to JR. Take any selection of solutions to each of these, then the Chinese remainder theorem puts them up, bundles them up together, and gives you a unique solution modulo n to the original problem. Okay? That's the way the overall kind of framework is going to be arranged. And each different selection of solutions to these, each different set of choices here will yield a different solution to the original problem. Also, if one or more of these sub-congruences, if they have no solutions at all, then the original one has no solutions at all. Because you've got one of these kind of cases here, you'll have no options for the solution Sij, if one of these here happens to have no solutions at all. So one of these has no solutions at all, then that busts the chances for the original thing to have solutions. So the remaining thing which we haven't described is how to solve each of these. Taking a general polynomial congruence modulo a power of a prime, this is the kind of missing step that we need to fill in. Okay, we've already dealt with the Chinese remainder theorem, and we've dealt a lot with the idea of congruences and co-primeness that allows you to put these sets of solutions together to get solutions to the original problem. So the remaining issue is, well, how do you find the solutions of these? If the power on the prime is 1, so if it's really just a congruence modulo of prime, not the power of the prime, but just p to the power 1, then we've got theorem 7.1 in this chapter, Lagrange's theorem, which tells us that this thing has at most p solutions. Sorry, at most n solutions, where n is the degree of this. So at least we've got partial information about how many solutions it can possibly have. We know there's no more than n solutions. So if we do start investigating this modulo a single prime, as soon as you find n solutions, you know that there can't be any more. So at least that limits the possibilities. But we still need a good way to be able to think about what happens when the modulus is not a single prime, but a power of that prime. And that's what theorem 7.2 allows us to do. Now, we're not going to prove theorem 7.2. It's a little bit overly technical, and I'd rather just make use of the result, see how it can be used here, and then make progress into chapter 8, which is a lot more interesting material, a lot more fun material, a lot more rewarding material, rather than working through the proof of this. Okay. Let's have a look at the results. Okay, so what this is about is how to get solutions to these. This technique is sometimes called a solution lifting technique. So let's have a look at what do I mean by solution lifting? Well, if we just read the start of it and the end of it, you'll get the idea of what solution lifting means. The assumption of the theorem is, consider this polynomial congruence modulo p to some power a minus 1. And it says, suppose this has a solution r. So suppose you've got one solution to this problem, f of x congruent to 0 modulo p to the a minus 1. Then ignore some of the detail here, but just look at the kind of results it gives you. In this case here, we'll look at the details of the case in a moment. The conclusion is, it says then r can be lifted to a solution of this one, which is the same polynomial but modulo p to the a. Ignore the fine detail for a moment. Or in this other case is two subcases. In one of them, that solution r to the original problem lifts to p distinct ways to give you p distinct solutions to f of x congruent to 0 modulo p to the a. So you're taking a solution r, which is a solution to f of x congruent to 0 modulo p to the a minus 1, and you're from it building solutions to f of x congruent to 0 modulo p to the a, modulo 1 extra power of the p. Or in this other subcase here, it tells you that r solution you had to f of x congruent to 0 modulo p to the a minus 1, it says it cannot be lifted. It cannot be associated to any solution to f of x congruent to 0 modulo p to the a. So that's what we mean by solution lifting. You start off with the solution to f of x congruent to 0 modulo p to the a minus 1. You follow the details here, and what you get is either a single unique solution to f of x congruent to 0 modulo p to the a, we've increased the power by 1. Or you can associate r to multiple solutions of this thing, modulo p to the a. or you find the R you started with cannot be associated to any solution f of x coming to 0 modulo p to the a. So it allows you to take solutions to one of these problems modulo a certain power of p and get solutions to the next highest power. So that immediately suggests a kind of inductive process to get solutions to f of x coming to 0 modulo p to the alpha. You start off and you try and solve it modulo p. Get solutions to the thing where the exponent is 1. And then you use this result to lift those solutions up to modulo p squared. Then you take those solutions to p squared, you lift those up to modulo p cubed, and so on. You keep lifting up solutions until you hit whatever particular power of the prime you're faced with. Okay? And then you have solutions to this intermediate sub-problem. Solve all of those, and you put them together with the Chinese remainder theorem, and you solve the original. So that's the overall kind of flavor of the result. Okay, now let's look at the technical details, and then pretty quickly then we'll work through an example. So as you say, the theorem starts off with a solution R to f of x congruent to 0. So R is a nice representative of a congruence class modulo p to the a minus 1. So it's some number between 0 and p to the a minus 1. And the first bullet point, there's two options for the first bullet point. There's two cases that you follow. What we do is we look at, so this f dash is the derivative of the polynomial. It's a little bit strange to see a derivative cropping up here, because a derivative is, you know, something you normally associate with calculus and analysis. So to see it popping up in this kind of discrete number theory sense is a little bit surprising. But anyway, we look at the derivative of the polynomial f. You evaluate it at R, the solution that we've got in our hand at the moment. When you evaluate it at R, you're either going to get something non-zero modulo p or something 0 modulo p. So depending what you get, you then follow that bullet point. Okay. So when you evaluate the derivative, if you get something non-zero modulo p, you go into this case. If you get something 0 modulo p, you go into that lower case. So let's look at this first case. When you do get something non-zero modulo p, that's the nice case where the solution R can be lifted to a solution S. Okay, to one unique solution S modulo p to the a. And moreover, it gives you a formula for constructing the S, which is based on R, the solution you have in your hand at the moment, to the previous level of exponent, plus t times p to the a minus 1, where t is the unique solution that comes out of this congruence here, which is a slightly reduced congruence using the derivative of the polynomial f and this term here, f of r divided by p to the a minus 1. Okay. On the other hand, if we get put into this second bullet point here, where we've got a something 0 modulo p, when you evaluate the derivative of f at r, then there's two cases when you look at the value of f evaluated at r modulo p to the a. If it's 0, then your solution R is going to lift in multiple ways. You actually get p new solutions to the next level of exponent, p to the a, for f of x congruent to 0. We've got a formula for them here. This gives you SI for I between 0 and p minus 1. So these are the p new solutions. They're all based on the value of R, and involving I and p to the a minus 1. On the other hand, see, that was if you got something 0 modulo p to the a. More typically, you'll get something non-zero modulo p to the a, and that's the case where R cannot be lifted any further. Okay, but the solution you have in your hand at the moment does not lift and yield any new solutions to a higher power of p in the polynomial. Okay? So as I say, we're not going to prove this as such, but we're going to make use of it. Okay? So we can have a look at this example 7.1. I know there's a lot to take in there, a lot of technical matters coming up, but hopefully it'll become clearer when we start working through this example. So it's very much going to be a case of following this kind of algorithm or recipe. It's a kind of decision procedure. You have some solution R to start off with. You test it against this black bullet point condition. Depending on which outcome you get according to this test, you then follow that bullet point. And the second bullet point has a further test. Straight line, bullet point, you test, depending on what outcome of this test is, you either have lifting to multiple solutions or not lifting to a new solution. Okay. So let's have a look at this example 7.1. So example 7.1, we're looking to solve f of x. F of x is equal to x squared plus 3x minus 16 is congruent to 0 modulo 81. And 81 is 9 times 9, or 3 to the power 4. So this is a problem like one of these subproblems that you face in a general, trying to solve f of x congruent to 0 modulo a general f. Okay, here we got the power 3 to the power 4. Okay. So we consider the bottom case first. And by bottom case, we mean f of x congruent to 0 modulo 3. Modulo that prime to the power 1. Now, when you're considering it modulo 3, this polynomial doesn't look nearly as intimidating, because if you're considering it modulo 3, that means you can reduce all the coefficients modulo 3. When you're working in the modulo 3 world, things are fairly simple. There's only 3 objects, 0, 1, and 2. Every integer is congruent to either 0, 1, or 2 modulo 3. So any of those coefficients you see in the polynomial that are not 0, 1, or 2, you can reduce them to their representatives. 0, 1, or 2 modulo 3. So this becomes the polynomial, well, x squared is still x squared. 3 times x, we can chuck that away, because 3 is 0 modulo 3. So having the 3 times x in there doesn't have any effect at all, because it's congruent to 0 modulo 3. And minus 16, well, we know a much simpler version of 16. It's namely 1. 1 modulo 3. 16 is congruent to 1 modulo 3. So that polynomial immediately reduces to x squared minus 1 congruent to 0 modulo 3. Can you identify any solutions to that? Well, that's x squared congruent to 1 modulo 3. You just go with your instincts. What are the solutions here?
1, 2.
1 and 2. Yeah. 1 and minus 1. Minus 1 is the same as 2 modulo 3. And if we wanted to, we could appeal to that theorem of Lagrange that said, for a polynomial congruence modulo a prime, the degree of the polynomial gives you an upper bound on the number of solutions. Well, here are 2 solutions we've found, so we know there's no more. Of course, we also know there's no more because the only other option modulo 3 is 0, and 0 is not congruent to 1 modulo 3. So 0 is plainly not a solution. I mean, there's not too much that can happen modulo 3. So, but in principle, an appeal to Lagrange's theorem convinces us that there's no more solutions. So x is congruent to 1 or 2. So this gives us 2 solutions to the bottom case of the problem. And it gives us 2 solutions that we can try and lift now to higher powers of 3 to ultimately try and find solutions to f of x congruent to 0 modulo 3 to the power of 4, modulo 81. Okay, so now we will make use of theorem 7.2, no, 7.2, with r equal to, so let's choose one of these solutions, r equals 1. And what we're doing is we're attempting to find out if this can be lifted, attempt to lift this solution, r equals 1, to a solution to f of x congruent to 0 modulo 3 squared, modulo 9. This is the 1 power higher on the 3. So you look at the statement of the theorem on there on page 52. Well, we need to take the derivative of the polynomial, which is 2x plus 3. And we need to evaluate that at r, which means to evaluate it at 1. And we get 5. And if you look at that, the black round bullet point, that's the decision to make. We just have to assess this value of the derivative modulo p and work out is it non-zero or 0 modulo p. Well, we've got 5. P is 3 here. So 5 is clearly non-zero modulo 3. So that means it's the upper case that we're in. Okay, we've evaluated the derivative at r. We've got a non-zero value. And so by theorem 7.2, solution r equals 1 to f of x congruent to 0 modulo 3 lifts uniquely, or lifts to a unique solution S to f of x congruent 0 modulo 9. I'm repeating myself a bit there, unfortunately. And not only does it tell us that it lifts, it tells us exactly what the solution has to be. Its S is, so you see the formula there, r plus t times p to the a minus 1. So our r is 1, t we don't know yet, and p to the power a minus 1 is 3. So it's 1 plus t times 3. And what's this t? This t is the unique solution to this other congruence, which is there in equation 7.11. So we have to find this t, where t is the unique solution in the range, well, it's either going to be 0, 1, or 2, and the unique solution to this polynomial, which is 5t minus 12 over 3, congruent to 0 modulo 3. So that's the congruence which is indicated in equation 7.11 on page 52. The derivative is t times the evaluation of the derivative minus the evaluation of the original polynomial f at r equals 1, which comes to 12, minus 12. So when you have 1 plus 3 is 4, minus 16 is minus 12. That's the minus 12. And then we divide that by p to the a minus 1. So in this case, that's 3. Because the a minus 1 is equal to 1. We're trying to solve this modulo 0, congruent to 0, modulo 3. Now it's modulo 3, so the 5 is the same as 2. 12 divided by 3 is 4, of course. 4 is just 1, modulo 3. So it's 2t minus 1 is congruent to 0, modulo 3. So in other words, it's 2t congruent to 1, modulo 3. And that's only true if t is congruent to 2, modulo 3. Okay, we can solve that directly because it's modulo 3. There's only 3 things floating around, 0, 1, and 2. But in principle, the idea here is where the coefficient on t is going to be coprime to the modulus. Okay, because the coefficient on t is the value of the derivative. We already know that's not congruent to 0 modulo p, so it is co-prime. So the coefficient on t will have a multiplicative inverse. So that means this linear congruence will have a single unique solution. You multiply both sides by the multiplicative inverse of the coefficient of t. 2t congruent to 1 modulo 3, t has to be 2. 2 times 2 is 4. It's congruent to 1. So that's our t equals 2, which feeds back into here. So we've got this solution S congruent to 1 plus 3 times 2. So S congruent to 7 modulo 9 solves f of x congruent to 0 modulo 9. So we have successfully lifted our beginning solution of r equals 1 up to a solution to the congruence modulo 9. The original problem asked for modulo 81, so we've got to keep going. So now reapply Theorem 7.2. We take this new solution we have, 7 modulo 3 squared. So with r equals 7, a is now equal to 3. Because the a minus 1 is the power on the prime that you're starting from. You're trying to lift up to modulo p to the a. So we're going to lift to the exponent 3. So now we check the f prime, the derivative evaluated at r, which is the derivative evaluated at 7. Look up a bit, we have the derivative 2x plus 3, so that's 14 plus 3, so that's 17. And well, 17 modulo 3, we reduce it modulo 3 is congruent to 2, which is certainly non-zero modulo 3. So again, we're in that first bullet point. So this solution is going to lift uniquely. So again, this lifts uniquely to a solution of f of x congruent to 0 modulo 3 cubed, modulo 27.
I mean, modulo 3 still 9 in this bit.
Here we're starting from a solution, modulo 9. And we're
There's a 3 in the middle.
that 3.
Yeah.
Yeah, but that's checking this condition on the derivative, which is always modulo the prime, just, I believe. Yeah, which is always just based on the thing modulo the prime. And it's non-zero. In other words, it's co-prime to the prime, so we'll have a multiplicative inverse. So that's this case where it's going to lift uniquely to a new solution. The new solution of this, so the new solution is S, and it's going to be 7 plus t times p to the a minus 1. So it's 7 plus 9t, where t is the solution of 17t plus 54 over 9 congruent to 0 modulo 3. This is the value of the derivative times t plus the value of the original polynomial f at this solution 7, which comes out as 54, divided by this p squared this time, p to the a minus 1. And considering that modulo 3, that's equivalent to, so that's 2 times t, 54 divided by 9 is 6, which is 0. So it's 2t plus 0 congruent to 0 modulo 3. And what solution does that have? That has the solution that t equals 0. T congruent to 0. It's the only way you can multiply 2 to get something 0 modulo 3. So in this case, because t has come out 0, that means that the new solution is just 7 again. So we now have a solution S equals 7 plus 9t, but the t is 0, so it's just S equals 7. A solution here to f of x congruent to 0 modulo 3 cubed, 27. We're nearly there, just one more step to go to get to modulo 81. So you just feed it in again. Just reapply theorem 7.2. Reapply theorem 7.2. Now our beginning solution is again 7, and A is now 4. So we've got a solution to modulo p to the a minus 1. Now we're going to finally lift maybe to modulo 81, 3 to the power 4. The derivative evaluated at 7 is still non-zero. That was the test before. That's equal to 17, which is certainly non-zero modulo 3. So again, lifts uniquely. To a new solution S, which is going to be 7 plus 27 times t, where t is the solution to, so our t equation now is 17t, that's the value of the derivative times t, plus the value of the polynomial at our intermediate solution 7, which is 54, this time divided by 27, to 0, modulo 3. But again, this has the solution 0 because 54 divided by 20. No, it doesn't. Excuse me. That's wrong. So reduce everything modulo 3. So that's 2 times t. 54 divided by 27 is 2. So 2 times t plus 2, so that means 2t is congruent to minus 2, which is congruent to 1 modulo 3. So t has to again be equal to 2. It's the unique solution to this. So that's our final t value. So that's going to feed in here to give us our new solution S. So we have a solution S equals 7 plus 27 times 2. I'm going off of that, which is 61. 54 plus 7. 61. To our original problem now, f of x congruent to 0 modulo 81. So that's the lifting process, where we start with solutions to the problem modulo 3, and using that theorem 7.2, it tells you how to lift them, how to associate new solutions to that previous solution to the next highest power of the prime. So now we would need to repeat the process using the second initial solution. Remember, we had 2 solutions to at the bottom level. Using the second solution on the bottom level, which was r equal 2. And we repeat that again. We didn't quite have time to do that today. But you lift that in the same way. Following the decision procedure here, and moving one step up, one power up all the time until eventually you get to p to the whatever the top is. And of course, there is a handout which comes with the exam with statements of results and so on, and please particularities that this whole result is stated there. So it's not something you have to memorize, but it's something you have to understand how to follow, how to apply it in certain cases. But we'll do some work with this in the tutorials on Friday. I'll see you there. Okay. That should hopefully leave us free for chapter 8 and beyond. The rest of the term. Okay.
I'm 5. After about 10 of